So thank you, Uwe, and thank you all for being here. So these last few years, I've been looking into ultrasound imaging of lithium-ion cells, and it has really turned out to be a method that changes the way we view batteries and helps us understand them in a way which hasn't really been possible before. So I'm excited to use these next 45 minutes to guide you through the process of how we started using ultrasound here, how we ended up here, how it works, and why we should use it on lithium-ion batteries. But first, let's have a look at what we're facing today. So this year alone, we are estimating roughly to have a lithium-ion battery demand of 1 terawatt-hour. And this equates to millions of electric vehicles being sold just this year. And considering we only started out using electric vehicles and stationary storage a few years ago, this is already an exceptionally high demand that we're having today. And we are very lucky that this demand is actually expected to further increase. So by 2030, we are projecting an annual lithium-ion battery demand of roughly 4 terawatt-hours. So everything seems to be going in the right direction. But unfortunately, if we are serious about our climate goals, which means being CO2 neutral by 2050, this lithium-ion battery demand is not really close to where it should be. We should be much more on this blue and gray curve combined. So we should be storing more renewable energies in either electric vehicles or stationary storage. But why are we not getting this demand? And the obvious answer here is that lithium-ion cells have been historically and to some extent are still today just too expensive to get this market penetration that we want. So the only way to solve this problem from like an R&D perspective is to somehow develop cells which are using inexpensive materials and are somehow easier to manufacture. And this is much easier said than done, because if we have a look at the current battery R&D cycle, we typically start out with a 1 to 3 year pre-development phase where you come up with your cell concept and then you iterate on this concept, improving it from an initial prototype to something that you can actually mass produce. And in order to accelerate this process and get these new battery innovations, which are supposed to be much cheaper, passed into the market, we need to accelerate this process. And to see what we can actually change, we need to go one step deeper. So, for example, within this A sample, we come from this pre-development phase where we develop the cell concept, so we know which materials are we going to use, and we have like the rough dimensions of the cell design. And then we actually start to develop and manufacture a few of these cells, sometimes incorporating manual manufacturing processes that just to get the first prototype batch as fast as possible into the validation phase. And this is something that we do a lot here at this institute. The entire third part of this building is mostly dedicated to this task. And here you can see one of our test benches. So all of these cables are connected to one of these prototype cells, and we just charge and discharge them hundreds of times. And after many, many cycles, we usually come to the conclusion that this initial prototype is typically not meeting the requirements, so we need to change something in the cell design or concept. But just using these electrical measurements, we typically do not have the information on what actually needs to change. So in order to improve our cell concept, we need to have a look inside the battery. And one way to do this is to actually disassemble it. And here you can see a video of somebody trying to open a 4680 cell with a pipe cutter. So you can imagine this is a very rough and manual process, difficult to automate. And even when you have highly trained personnel, there's a lot of things that can go wrong here. But let's assume you're successful with your cell disassembly. Then you end up with this jelly roll that you need to scan through and identify any malfunctions that you weren't expecting. For example, a very strong aging mechanism or any manufacturing defects. And then you take samples of any suspected aging events that you were anticipating, and you put them in this very expensive microscope, and you discuss with your R&D team what you're seeing in this microscope and how you can prevent these effects from happening in this next iteration phase. And you can imagine that this cycle is a very long and tedious process. We're using an expensive microscope. There is a lot of highly trained personnel here that has to do this work manually. And if we would somehow find a way to visualize the inside of the battery non-destructively and much earlier in the process, we could feed back this information to the next iteration cycle much quicker and with less financial resources. So this is our mission statement here. So we can accelerate the cell development by looking into the battery early in the process. And if we have a look at what is already available on the market, I don't want to get into all of the nuances of these imaging methods here, but there seems to be a trend where you have really expensive imaging techniques, for example, X-ray imaging or neutron imaging, which typically generate the best images that you can get. And as an example, for the other side of the spectrum, we have something like infrared imaging, which is very inexpensive, widely used, but only gives you like surface level information during cell operation. So there seems to be an obvious gap here. And we're looking to really scale this cell development procedure. We're looking to find an imaging method that is low cost and has a good enough spatial resolution to answer the questions that we have and provide the feedback. And when I started my PhD, this gap wasn't really filled, and researchers have been looking for a long time to find the answer here. And but luckily, we got a hint of what might work, as with any good discovery, by accident. So Dan Steingart, my co-advisor here, who will be joining us later today, accidentally, so the story goes, knocked a few batteries off his desk, and he observed that some of them, the fully charged ones, didn't really bounce, and the discharged ones bounced out a lot. And he asked himself, what is this bounce telling us? And we know from electrochemical fundamentals that these types of batteries change their density distribution and their Young's modulus during cycling. So they go from this dry and hard paste when they are fully charged to this soft, lumpy mass when they are discharged that looks like gelatin. You might also say they behave like a rock when they are fully charged and like a rubber ball when they are discharged. And these types of drop tests are great for like an initial demonstration, but they are difficult to reproduce when you have different cell designs. And we really need something that is more quantitative. And we also know that ultrasound is very sensitive to these density distribution and Young's modulus changes. So maybe ultrasound is the way to go here, because ultrasound has a lot of other beneficial properties. For example, it has been used in the medical field for decades, so we can just go ahead and buy commercial devices and just immediately apply them onto our batteries. And it's very low cost. That's why it's so widely used. Very safe because it's used on humans. So it really seems like a good candidate here. And this is where my PhD thesis comes in. The task is to answer this question: can we visualize the inside of the battery using ultrasound and see any effects that are interesting to us during this R&D development cycle? So let's actually try to prove this concept that ultrasound is in fact capable of verifying first this bounce experiment, so we know that we are at least getting the same information that we can immediately visually verify. So in order to measure ultrasound, we first need to produce sound waves, and typically we use piezoelectric materials. These types of materials change their structure when they are in an electric field. So when you, for example, apply a positive voltage on them, they, for example, increase in thickness, but when you then suddenly disconnect this voltage, they jump back to their original size. And if you do this disconnection fast enough, the elastic properties of the material and the inertia actually make the material wiggle and produce this sound wave here. And in practice, we use high voltage, so over 100 volt and very short pulses, less than 1 microsecond, to apply on these piezoelectric materials to produce a sound wave. We then force the sound wave onto a battery. It passes through it, interacting with all of its components, and then is transmitted on the other side. And when we would now place a second piezoelectric material in front of this transmitted ultrasound wave, it would act as a force on this piezoelectric material, compressing it, and therefore using the same effect, also generating this voltage. So this is how we can produce and measure ultrasound effect. We call this right effect the direct piezoelectric effect, and the left one inverse, because just the right one was discovered first. But if we keep the focus now on this verification of this bounce experiment with ultrasound, we need to apply this concept on a real battery cell. So here you can see an image of the of the test setup that we have constructed, and we actually glued two piezoelectric materials facing each other on opposite sides of this battery cell, so this blue thing here, and we connect our cables and start to cycle. And if we now want to observe the mechanical effects changing within the battery cell during cycling, we need to analyze this transmitted sound wave, because this is the one which has actually interacted with the battery. So here you can see an example of such a ultrasound signal which has been transmitted through the battery. And if we want to track its changes, we first need to zoom into the first 12 microseconds. And here we have two important features that we are going to analyze throughout the rest of this presentation. So the first one is time of flight. This is just the time it takes for the sound to pass through the battery. Usually when we have the battery which is wider, the time of flight increases because the path just gets longer from the sending piezoelectric material to the receiving one. And then there is the second feature, the amplitude, also typically decreasing with wider cells, because the active material within the battery is actively dampening the sound wave, extracting energy from it. And if we would now track, for example, this time of flight change during cycling, we end up with this graph here. So this orange curve is the voltage of the battery, and the black one, the time of flight. And we can immediately see that when the cell is fully charged at these high voltages, we have a low time of flight value. And when we discharge the cell, the time of flight is increasing. And when we charge the cell, it's decreasing. So there seems to be this inverse relationship here. And we know from physical fundamentals that the time of flight is closely linked to the Young's modulus and density of the cell over the speed of sound. So we can just look up this equation which connects these two parameters. And if we just insert our time of flight values into this equation, we can calculate the Young's modulus. So when we have a high time of flight, typically occurring at low stages of charge, we have a low Young's modulus, which is this rubber ball behavior. And when we have low time of flight values at high stages of charge, we have this high Young's modulus, which is this rock behavior. And in order to understand why this change is happening, we need to have a look at the material level. And we know from prior studies that most of the mechanical change within the battery is occurring at the anode. So if we now have a look at a fully discharged anode, we have these graphite layers. And if we would now charge the anode, the lithium ions would be placed nicely in between them until there is no more room for any additional lithium left. And this is how a fully charged anode then would look like. And I think it's pretty intuitive to understand that this right material here with all of the lithium between the graphite has a very different density and Young's modulus than this left material. So this actually verifies that we can reproduce this bouncing experiment with ultrasound more quantitatively. So we're at least getting the same information in this bounce test. And this is great, but there is this widespread hypothesis in the industry that most of the really bad aging effects that you really want to prevent during battery operation are not really happening homogeneously throughout the battery. So typically you have some local design flaw or some inhomogeneity, maybe a manufacturing defect somewhere, for example, in the edge here in this corner of the battery. And if we just measure the ultrasound here in the middle where everything is nice and homogeneous within the cell, we're not really able to capture these aging effects or mechanical changes happening at the edge. And now I just want to introduce to you a few aging mechanisms that are actually typically occurring locally distributed within a battery. They can also occur homogeneously, but typically when we have a design flaw, they occur locally. And if we now start from a pristine cell with only one anode and one cathode, so this is like a simplified cross-section of such a cell. Here, it wouldn't matter where we place our ultrasound sensors, because if the cell is perfectly homogeneous, all of the electrochemistry should be homogeneous as well. And so now, just to introduce a few aging effects, you don't need to understand them all in detail. We will do this later on in the presentation. But if we would just now introduce a local design flaw within the cell or a manufacturing defect that is, for example, blocking the pathway between the cathode and the anode, preventing lithium ions from intercalating into the anode, and, for example, just being deposited on top of it, we would get this local deposition, which is this brown part here on the top of the battery. So typically, these deposits consume a large chunk of lithium, which is then not really longer usable for further cycling. So this is something that might occur locally, and we really want to prevent. And another typical local aging effect is gassing. So again, if you have some unwanted electrochemical effect between the electrolyte and the electrodes, which is somehow locally motivated, there can be gas be produced, and you can also imagine that you do not want this gas in your battery cell because this gas accumulation is blocking lithium ions from traveling between the cathode and the anode. And then this last aging or defect in this case is just like a mechanical manufacturing defect. So let's just assume a chunk of the electrode is missing here, or another very prominent example is this Galaxy Note 7 battery fire that you saw maybe a few years ago. Here, a local manufacturing defect actually caused the battery to short circuit locally, causing detrimental effects throughout the whole battery, heating it up, and eventually the whole battery catched fire, causing multi-million-dollar recalls. So this was just to motivate that it is not sufficient to just measure the ultrasound in the middle of the cell. So we need to expand our viewing window from this small red square here in the middle to the entire cell surface. So this is what we're going to focus on in this next part of the presentation, the imaging part. I'm going to show you what are the devices that we developed to do this imaging, how this whole thing works, and the first few results. So this is the device that we developed in my first year here as a PhD student together with Niklas Kissler. It basically works like a 3D printer, but instead of printing things, we are applying ultrasound sensors at the arms, and we are then moving these transducer here. So one is on this side of the cell, and the other one is on the other side of this battery cell. And the stepper motors are doing this movement, and we are doing this one-dimensional ultrasound measurement throughout the whole cell. And then we, in order to not to touch the cell during this movement, we apply silicon oil onto our apparatus. This is just to conduct the sound wave between the transducers and the battery cell. And if we now start this measurement process, you can see the transducers moving across the battery. I'm not going to show you the whole video because this first instant of imaging took more than 30-40 minutes to generate an image. But it was only a first demonstration, and we didn't really focus on increasing the speed of this movement, but we are just trying to demonstrate if we can actually visualize the core of the battery in a meaningful way. But we definitely recognize the huge price advantage that this device had, because we only invested less than 5,000 euros into developing this device, including all of the electronics and mechanical hardware. So in order to verify whether this device is actually working, our former colleague Jörg Fuchs gave me the cell, and he came to me and told me that this cell is somehow aging much faster than he expected. And he asked me to take this ultrasound image to visualize what's inside of the cell and if we can see anything that might explain this fast aging speed. So this is the first ultrasound image that we generated from this pouch cell, and we can see, first of all, this outline of the battery cell is pretty well visible in this ultrasound image, but besides this yellow plane, we see a bunch of blue and green islands scattered across this battery cell. So in order to understand what we're seeing here, we need to go one step back and understand the underlying ultrasound fundamentals. So if we again revisit this simplified two-dimensional battery cell with only one anode and one cathode, and we further assume that there is a ultrasound wave coming from the left, so with the amplitude AI, this incoming ultrasound wave. And we know from the ultrasound fundamentals that whenever there is an ultrasound wave traveling between two materials, there will be a reflection and a transmission at this material interface. And we can calculate the amplitudes of this reflected and transmitted part using the so-called acoustic impedance. And this is just an umbrella term for the density in Young's modulus of a material. And we can use these equations down here to calculate the reflected and transmitted part. So you might recognize these equations. These are the same equations that we use whenever there is an electromagnetic wave traveling across a wire, for example, in a PCB, and which might also interact with a material interface. So if we now assign acoustic impedances to each material within our apparatus, so Z0 is the silicon oil, Z1 the cell housing, and so on, we can now calculate the individual reflections happening during our measurement. So the biggest material mismatch we have in our apparatus is the interface between the silicone oil and the cell housing. So we go from a liquid material into some solid, so very different acoustic impedances, and we get a pretty large reflection at this interface. And then we need to subtract this reflected amplitude from the incoming amplitude, and we end up with this transmitted ultrasound wave in the middle. And if we for now assume that all of the acoustic impedances within the battery are pretty similar, because there's this porous material and we just drench it in electrolytes, so everything is fairly homogenized within the battery, we don't get any major reflections within the cell. The next major reflection will occur when we try to exit this battery on the other side. So again, we have this very large mismatch between the solid material from the cell housing and this liquid electrolyte. So we end up with this transmitted ultrasound wave here, which is obviously lower than the incoming ultrasound wave. And if we now introduce a deposit layer, so this aging effect that we saw earlier, we will again have this reflection in the beginning and end up with this transmitted wave. And if we now assume that this deposit has a slightly different acoustic impedance than the rest of the battery, we will actually get another reflection at this material interface between the battery materials and this deposit, further lowering the transmitted ultrasound wave from this initial gray sound wave to this blue one. And the same thing works for a mechanical defect. For example, let's assume we have parts of the cathode missing, and this hole is just filled up with electrolyte. Then again, we have a pretty large material interface, acoustic mismatch within the battery, and we get this fairly large reflection within the battery, further decreasing the transmitted amplitude. And this last example is a gas accumulation that I showed you earlier. And gases have very different properties than both liquids and solid materials. In fact, they have a very much higher acoustic impedance than all of the other materials within our battery. So we will not get any transmission at all, but only a very large reflection. And this is also true if we would now introduce a deposit underneath this gas accumulation. So because this gas is reflecting all of the sound wave, we are not able to interact with this deposit underneath this gas accumulation in any way. So just to sum this up, we have ultrasound dampening in a homogeneous material, and whenever there's a material interface, we have reflection and transmission, and if we have very different materials, the reflection is pretty high. So if we now revisit this ultrasound image from earlier, we can now with more confidence say that this whole yellow plane is probably fairly homogeneously aged battery with not too severe aging here, and these blue and green islands seem to be a gas accumulation in this blue case because we don't have any signal penetrating the battery, and this green one is probably some deposit or manufacturing defect or a combination of the two. And the only way to verify this is to actually disassemble the cell and take a picture of what's inside. And this is the optical image that we got from the anode. So we were very excited that these two images are so congruent. So this method seems to work. We seem to actually be able to visualize what's inside the battery. But there is one problem here. First, we hypothesize that there is a gas accumulation in this lower left-hand corner. But if we actually look at the optical image, there seems to be a deposit here. So this is exactly this gas problem that I was talking about earlier, because we are only generating two-dimensional information. If we have any aging effects overlapping each other, we are not able to distinguish between them when we use this transmission mode ultrasound imaging. But still, this image looks pretty well, and we are quite happy with it. But if we take one closer look at one of these deposits, they seem to be surrounding this inhomogeneity here, so these round brown circles here. And this is really interesting to us because we earlier hypothesized that those really strong aging effects that we want to prevent within battery operation are coming from local design flaws or inhomogeneities. And we talked to a bunch of manufacturing people, and they confirmed to us that this is most likely due to a not optimally performed Z-folding procedure. So Z-folding is a really important step during battery manufacturing. This is where you stack all of the cathodes and anodes on top of each other. And in order for the battery to work the way you want it to, all of these electrodes need to be aligned perfectly. So in order to make their lives easier, a few manufacturers feel the need to apply a locally distributed adhesive. So these are these dots here, we assume, just to have half of the electrode stack not move during the stacking procedure. And you might imagine that this, if not perfectly tuned, might mess up the local electrochemistry. So in order to understand what's really happening here, let's have another look at this anode. And next to it is this illustration of what we believe is happening during cell assembly. So we have this anode and this these adhesive dots that are supposed to glue the anode to the separator. And now we need to understand what the difference is between an anode which is charged homogeneously and one with it which is charged inhomogeneously, for example, by this locally distributed adhesive that is impeding the lithium-ion flow between the cathode and the anode. And we already talked about the homogeneous case earlier. So this is this graphite structure, and those lithium ions are being placed inside this graphite structure. And when there is no more room left within this anode, we typically start this process, and we call this 100% state of charge. But if we now have this inhomogeneity in this anode, which is blocking the lithium ion flow, causing this higher lithium ion flow at the edges of the adhesive, you can imagine that if the battery is not designed for this high current to happen at this perimeter of this adhesive, that the lithium ions do not have the time that they need to place themselves into the anode, and then unfortunately have to be deposited on the surface of it. And we call this effect lithium plating, and there's a bunch of literature on why this is bad and why we should avoid this. But this effect is not only interesting for people who want to design cells, but also for people who want to design fast charging processes, because you can imagine if you are not only locally fast charging your cell, but homogeneously fast charging a pretty homogeneous cell, the first instant of lithium plating will probably happen at the smallest possible inhomogeneity within your battery. So if we somehow are in fact able to visualize this lithium plating with our ultrasound method indestructively, this would be a great benefit, because there isn't really any method on the market that then can do this small lithium plating detection, which is also only happening locally distributed. So in order to prove this point, we did a scanning electron microscopy image that you can see here. So this is right at the border between the adhesive and the anode. And this is the border that was between this adhesive that you can see here. This is this shiny part. And if we just compare the side of the anode, so this is where we suspect this lithium plating, to literature images of lithium plating, we can basically see that they look very, very similar. So we are in fact validating that this is most likely actually lithium plating that we're seeing here. But if we now strip away part of the adhesive, we can actually see that under this adhesive is perfectly pristine graphite, which looks like it has never been even cycled before, further confirming our hypothesis that this adhesive is actually blocking the lithium ion pathway and only allowing lithium charging to happen at this perimeter. So in conclusion, using ultrasound, we can measure effects which are related to fast charging and this local inhomogeneities. But yeah, this is really exciting, but we encountered two major problems in this chapter. So the first one was this overlapping aging effect. So because we are only generating 2D images, whenever there is overlapping aging effects, we can't distinguish between them. So we need some kind of depth resolution to be able to do this. That's the first problem. And the second one is the scanning speed. So if we are in fact trying to help somebody parameterize its fast charging process, we only generate one image every 30 to 40 minutes, you can imagine that the fast charging process will be over by the time we have generated our first image. So this is not really helpful. And we actually solved this second issue by just using faster scanners, faster motors. You can see them in the first row. We bought this commercial device which can do the scanning very fast, so going from 30 minutes imaging to 30 seconds. So we are basically real-time capable now with imaging ultrasound. And the next part of the presentation will be dedicated to this first problem we encountered. So this 2D imaging problem that we need to solve by implementing depth resolution, or we can also call it 3D imaging. So if we revisit this two-dimensional simplified battery cell with this deposit in the middle, and we get all of these reflections and transmissions we discussed earlier, and we now introduce a gas accumulation on the rear end of this battery, we will get a complete reflection of the sound wave, which makes this deposit not measurable for the receiving transducer on the other side. But the information is still being generated here because we are still getting a reflection. So if we would now just analyze the reflected part instead of the transmitted part, we would in fact be able to measure the reflection at this deposit. And if we now have another look at this measurement from this reflection point of view, we would first emit an ultrasound wave, and because of the limited speed of sound, we would have to wait a few microseconds where we get our first reflection here at the surface. So this is where we have the surface information, and when we wait a few more microseconds, we get this deposit information, and then after a few more microseconds, this gas information. And if we now just connect this time domain to the depth domain, we are in fact just able to assign reflections that are happening within a point in time to a depth within the battery cell. So this is what we did in our latest work. Here you can see one of our reflection mode transducers that we used for this. And these reflection mode transducers have an additional benefit because they are also additionally focusing the sound wave in front of them and narrowing down the sound beam by a width of just 75 micrometers. So this increases our spatial resolution because now we can have a pixel every 75 micrometers, so we can get those really sharp images. And if we now analyze this reflected signal, we see all of these individual reflections, which we assume are coming from individual material interfaces within the battery. So if we translate this time domain to the depth domain using the speed of sound, we can divide the signal into gates, and each one of these gates is supposed to visualize one of these deposits. And if we only analyze now this part, which is interesting to us, so for example, the deposits we saw earlier, and assign a color map to only this one gate that is interesting to us, we should in theory be able to visualize what we want. And this is what we did together with a project partner. We tried to reconstruct this battery cell we saw on our first image with these adhesive dots and this Z-folding procedure, and we tried to make a battery cell which is really close to what we saw first, and now visualize it using our reflection technique. So we got a bunch of cells from them, we put them in our scanner, and if we would now just scan this marked area here, for example, using our method described earlier, we would get this image down here visualizing one slice within this 3D image. So this is, for example, the first anode being visualized. So if we want to visualize lithium plating to assist during fast charging processes, we need to charge the cell and make these ultrasound images in real time. And on the left side, you can see the ultrasound images, and on the right side, you can see the associated electrochemical procedure, so the fast charging protocol here. And when we now start to charge the cell, we can see those indications arising exactly where they were in the first image, so around these adhesive dots, and they actually grow during charging. So this is giving us a good hint that this is actually lithium plating, because this is very typical behavior for lithium plating. And if we now discharge the cell, we can see those indications shrinking. So as I mentioned earlier, not all of the lithium is actually trapped when we deposit it on the anode surface. We can recover a small portion of it, and this is what we are seeing here. We call this effect also lithium stripping. So we are actually using some of the lithium that was deposited for further cycling. And within the next charging step, we see those indications growing again, confirming that this is actually a reproducible effect here. And again, we need to verify whether this is actually lithium plating that we're seeing here in our ultrasound image. And again, we disassemble the cell, we compare the optical image to the ultrasound image and get again this visual congruency. But in order to verify that there is actually lithium plating happening here, we again made this scanning electron microscopy image, which again verified that there is actually metallic lithium being plated only on the perimeter of this adhesive and not anywhere else within the battery. So in conclusion, we can measure spatially resolved lithium plating in real time, and this can obviously be used to design fast charging algorithms. So you can, without any prior knowledge of your battery cell, you can just start charging it, make these ultrasound images, and when you see this indication happening during the fast charging process, you would tune down your charging current, and very quickly and without really any prior knowledge of the cell get to a semi-optimal charging procedure, which might actually also accelerate the development process of charging processes. So in conclusion, did we fill this gap that we are trying to fit earlier? So did we find a measurement method which is low cost and generates images which are meaningful for us in an acceptable time? And I think the research suggests that the answer is mostly yes. So we have obviously this very low-cost design that I showed you earlier, and we have this spatial resolution of 75 micrometers that we demonstrated in the second imaging phase. But whenever we would have to image manufacturing defects or any other effect within the cell which is smaller than 75 micrometers, we would really have to tune down the spatial resolution. And typically, there is always a balance with ultrasound between spatial resolution and penetration depth. So if there was a defect buried within a very thick battery, the dampening of the ultrasound wave would be so high that the sound wave would not have enough energy to have a sufficient signal-to-noise ratio when it is reflected back at the receiving transducer. So this is most likely something that can be solved in the future with different sensors, but to this date, this is still a barrier that we need to overcome. And as an outlook, I want to show to you a few images of prismatic cells that I generated, because this was the most common question I always got: does it also work on prismatic cells? And yes, this works very well. You can see an image of a prismatic cell down here, and we did this image on dozens of these prismatic cells, and most of them look like this one on the left, so pretty pristine, nothing really interesting happening here, pretty homogeneous. But by accident, we found one cell which had this line indication here and those two holes. And we further assumed by an ex situ analysis that this line defect and these two holes are actually mechanical defects in the electrodes during coating. So this motivated us to try and introduce this ultrasound imaging technique in the manufacturing process of lithium-ion cells that you can see here. And the image that we just generated could, for example, be used in an end-of-line testing after all of the manufacturing processes have been performed, to not build such a defect cell in a battery pack, which then might cause problems during operation. And this is great because we are preventing these things from happening, but it will be really interesting and much more useful to somehow find a way to visualize these defects much earlier in the production process, because you don't want to invest too much resources and energy into a battery cell that you are going to scrap anyway. So this is what we are going to work on in the future, somehow implementing ultrasound transducers into the coating process of battery cells. So including these transducers in the pipe, which is conducting the battery slurry from the mixer to the slother, which is doing the coating. Here you can see a close-up of these transducers at the end of this pipe. And yeah, the goal is to detect these homogeneities, because we demonstrated earlier that ultrasound is very sensitive to these gas accumulations and foreign particles. So we are very confident that this could actually provide useful information to battery manufacturers. So this concludes my talk.